And here are the notes on friction and gravity. It's going to be about half friction, half gravity, 2 slides each. We found on pages 36 to 43 of your book. And again, feel free to highlight in your book, jot down notes on the margins of your book, or if you want to write the notes on notebook paper, that's fine too. You're going to find some of the material in the gravity section is review, which is good. Okay. To start out, friction is a force that affects 2 surfaces. Okay, they're rubbing together. It can be 4 different types of friction that we'll get into here in just a minute. Okay, but we have two surfaces coming into contact with each other. Okay, the 2 factors that actually affect friction are the types of surfaces involved and how hard we push those surfaces together. If we have 2 really smooth surfaces like the tile floor and flat shoes that don't have a lot of the little bumps and grooves on them, you're going to slide pretty easily. Okay, again, it's smooth on smooth. Think about sliding on ice. Okay, smooth surfaces tend to have a lot of slip, so there's not a lot of friction there, not a lot of force. Rough surfaces like old shaggy carpet or the really bumpy like concrete or road surface, even like a dirt road or rock road, okay? That's what we call the type of surfaces, okay? Is it smooth, is it rough, is it soft and just kind of frilly, okay? Those are the types. And then how hard do we push those surfaces together also affects the force of friction. The harder they're pushed together, the stronger the force is, the greater the force. Okay, the bumpier the surfaces, the more friction there is. Okay, it acts in a direction opposite to the direction of the motion. Meaning, if we're pushing a box across this way, okay, we've got the green table, the bluish purple box, and we're pushing the object this way, okay, that's the object the motion's going in, friction acts in the opposite direction. Okay, so motion this way, friction in the exact opposite direction. Okay, if something's moving up, friction's acting down. Okay, if we're sliding across an ice rink and we're going that way, friction acts in the opposite direction. So one of our types of friction is called sliding friction. This is just 2 solid surfaces sliding over each other. Okay, sliding on ice, sliding across the tile floor, pushing a sheet of paper across the top of the table. All sliding friction. Okay, sliding down a hill on snow. Okay. Static friction is between 2 objects that aren't moving. Okay, a sheet of paper sitting on a table. There's actually friction acting between those. Book sitting on the floor. Me standing on the floor. I'm not moving, my feet are staying still. There's static friction between my feet and the floor. Okay, in this case, a big rock sitting on another rock. Fluid friction is the 3rd type. This is a solid object moving through a fluid. A fluid is considered air or a liquid. So we could have a bird flying through the air is fluid friction. A fish swimming in water. A ball, maybe a baseball or a football being thrown through the air. All fluid friction. A solid moving through air or a solid moving through water. Okay? And then rolling friction, okay, an object is rolling across a surface. Wheels on a car. Maybe it's a little toy car. Maybe it's rolling across the floor or rolling down a ramp. That's rolling friction. Maybe it's your bike tires on the sidewalk. If it's rolling like a ball or a wheel, it's rolling friction. Okay? That should wrap up the friction part of all this. We're going to do some stuff with this in class, a couple little activities. Okay? Next is gravity. This is a force that pulls objects towards each other. Okay, in fact, gravity is acting on all of us. It's acting everywhere in the universe. It's actually attracting you to every other person in the room. It's attracting you to the chair you're sitting on, if you're sitting on a chair right now. It's attracting me to the floor. Heck, I'm even being attracted to the smartboard. Is it strong enough to where I'm like plastered up against her like a magnet? No. Okay, but it is pulling everything together. Okay? The law of universal gravitation says a force of gravity acts between all objects in the universe that have mass. Okay? Even a little tiny speck of dust has a little tiny bit of mass. So that itty bitty little speck of dust is still being attracted to us. But again, it's not strong enough to act like magnets, but there is a force of attraction there. Okay? The two factors that affect the gravitational pull on objects is the mass of the objects involved and how far apart they are, the distance between them. Okay? Think magnets. Okay? The bigger the object, the stronger its pull on other objects. Okay? Just like a magnet. Bigger magnets have a stronger pull on other magnets or other objects. A smaller distance means a stronger gravitational pull, meaning we get them closer together. Think magnets. You bring two magnets close together, they really start pulling on each other when they get closer together. You get them really far apart, and they're probably not going to be pulling too hard on each other. Okay, think about Earth. If you're basically within the Earth's atmosphere, that's what we call the Earth's gravitational pull, and you're up in the sky, you're going to fall to Earth because of Earth's gravitational pull. You get far enough away from Earth, and you're going to be floating out in space. So generally speaking, our atmosphere is kind of the boundary of Earth's gravitational pull. It's what Earth can hold in. Okay, remember, mass is the amount of matter in an object. Okay, so the more mass there is, think of it as being like the bigger the magnet. Okay, so here's two small little objects. The force of gravity is acting between them. We make those objects bigger. The arrows have to get bigger, remember. Think back to last video. Stronger force means a bigger arrow. We have the objects getting bigger now, so the force gets bigger. Okay, now we're going back up to these two again, but this time we're going to pull them apart. That means it's a weaker force. The distance got bigger, so they don't pull on each other as strong now. So now we have to make the arrow a little bit shorter. Okay. Weight. Remember, is the force of gravity on that object, on the matter, okay? On the mass of that object. But again, weight includes gravity. Okay, if we go to a planet or an object like the moon that doesn't have as much gravity, it's not as big as Earth, so its gravitational pull is less. And you still, let's say we're on the moon and you stand on a scale, you're not going to weigh as much on the moon as you do on Earth. Is it because you got smaller? No, it's just there's not as much gravity. That force of gravity is less, so you're not being pulled onto the scale as hard, so the numbers aren't going to get as big on the scale. Okay? Your mass stays the same no matter which planet or solar system or anything you are in, which galaxy you're in. Okay? Your mass stays the same. Okay? It's the weight that depends on that gravitational force. Okay? So going back to the moon example. You weigh about 1/6 of what you do on Earth if you go to the moon, which means take your weight, divide it by 6, okay? That's your weight on the moon, okay? You don't want to know what mine would be. Or if you want to imagine going to Mars, take your Earth weight and divide it by 3. Okay, and again, you don't want to know what mine is, okay? But Mars is a little bit smaller than Earth. But it's also not as dense, it's not as packed as tight, so it doesn't have as much mass. Because it doesn't have as much mass as Earth, it has less gravitational pull, which means you go stand on a scale on Mars and you're only going to weigh 1/3 of what you do. Okay? This little diagram's in your book, so using this you could actually go figure out how much little doggy here weighs on each one of those objects. Okay, it weighs 60 newtons. Okay, notice we're now using newtons because we're talking forces. 60 newtons on Earth. So if we took 60 and divided it by 6, that's what little doggy would weigh on the moon. Okay, and then you can take the 60 newtons here on Earth and divide it by 3 to get what little doggy here weighs on Mars. Okay, Now, for reference, okay, if you're curious, 1 pound is about 4.5 newtons. Okay, I did some rounding there, but I've had some kids ask for the years. So if you ever want to do a conversion, there you go. Okay, each pound that you have is about 4.5 newtons. So you could take your weight times 4.45, 4.5, right in there, and get your weight in newtons. That would be the end of friction and gravity.